Okay, let's talk now about plane waves in the frequency domain, since we considered the time domain solution in the previous video. All right, so let's go back. These were our this was our wave equation over here, where we had the second spatial derivative of the electric field is proportional to the second time derivative of the electric field. I'm going to rewrite that over here, and then we're going to recast that in a slightly different form. All right, so that was second derivative of the x component of E with respect to distance. And again, we're assuming that we have propagation in the z direction, in a positive z direction, equals negative epsilon mu times the second derivative of the x component of E with respect to time. All right, now, one thing that we had figured out earlier when we talked about phasors was that taking a time derivative, if we convert that into the phasor domain, is equivalent to multiplying by j omega. Right? So here we've got a second time derivative, which means it's as if we're multiplying the phasor of E by j omega and then j omega again. So let's rewrite this in phasor form, and it's gonna look like this. D squared Ex, I'm gonna put that little squiggly line to indicate that it's a phasor, divided by dz squared equals minus epsilon mu times omega squared times the x component of E. And because when I square that j, I get a -1, this becomes a positive, right? So this is the wave equation at one frequency, right? It's a frequency dependent, or the phasor form of the wave equation. And the general solution to this, and we're not going to go through the details of how you figure it out, but the general solution to this is going to look like the following. That the electric field in the x direction as a phasor is going to be some base value, some base phasor value, times E to the minus j beta z, and it'll be oriented, let's say for now, it's in the x direction. All right. In fact, if we do that, then we can get rid of this x because it's already implied by putting an x hat right here. All right. If we do that, then we can use the same relationships that applied before to figure out that the magnetic field will be equal to that phasor value, that phasor constant, divided by eta times E to the minus j beta z, and that will be pointed in the y direction. Now, beta can be written a few different ways. Beta is the same as the wave number that we talked about way back in transmission lines. It has units of radians per meter, and we can write it as 2 pi divided by the wavelength, or we can write it as omega divided by the propagation velocity. But there's one more form for it, which is a little more convenient, which is omega times the square root of mu times epsilon. These are all the same, these three right here, at least for this condition. And it tells us how the phasor of this wave is changing as we slide along left to right. If we have observers in different places measuring this wave as it goes by, then beta tells us how much phase difference the two will observe, right? And so the same way as we dealt with this in terms of transmission lines, this beta z represents a phase difference, a phase shift between 0 and z. And this e to the minus j beta z is going to rotate the phasor in the negative direction by precisely this angle beta z. That's how much we're going to rotate it. And that accounts for the delay time, that the fact that the wave is going to arrive 1 meter in the at z equals 1 later than it arrived at z equals 0. That's basically accounted for as a phase shift. Right. Notice again, we still have that the electric field is perpendicular to the magnetic field. And I'm going to expand a little bit more on what we said before, we also know that the electric field cross product with the magnetic field points to the direction of propagation. Right? These two conditions are, for uniform plane waves, always going to be true. Right? That E cross H is in the direction of propagation, not the negative direction of propagation, but the direction of propagation. That's always going to be true. Right? Let me help you visualize a uniform plane wave. So here's a nice video right here, so you can sort of see it. Remember, the idea of a plane wave is that nothing is varying in the plane that is perpendicular to the direction of propagation. So if the direction of propagation is z, then nothing is changing in the x or y direction. They all have the same phasor value of electric field and magnetic field. But if you look at this in the time domain, as shown in the bottom right, what you're basically seeing is electric field and magnetic field that are orthogonal to each other, and the vector E cross H is pointing in the direction of propagation. It's a little bit hard to see or visualize, but what's actually happening is that the electric fields and magnetic fields are in fact wrapping around each other. That does happen as dictated by Maxwell's equations, and that wrapping around each other causes this wave to move. Right, so here's another way to show it with a slightly different animation. And let's say at the end of this line right here, you are observing the electric field and magnetic field. What you're going to see is a sinusoidal oscillation in the electric field and a sinusoidal oscillation in the magnetic field, but they'll be pointed in different directions. They'll be orthogonal directions, right? And the electric field crossed with the magnetic field at any moment is going to be in the direction of propagation. You can also see that if you measure the same sine wave at two different locations, you measure it once right here where you actually see it measured, and once right there, you'll see the same sinusoidal variation, but there will be a phase shift, and that phase shift is going to be beta times the location difference between the 2 points. That's going to be the phase shift between points A and point B. All right, so in that sense, we've now taken a look at how plane waves propagate and how they seem to work in the frequency domain. But we have continued to rely on this assumption that we can have propagation in the positive z direction, and then the mass sort of falls out nicely. The electric field is in the x direction, the magnetic field is in the y direction. We can in general do that. But we can't always do that, because let's say we have an example where I've got a piece of metal right here, and I've got a wave that's going to reflect off that piece of metal and go in this direction. There's no convenient place that I can set up the z-axis such that the plane wave is always propagating in that direction. So we need a more general formulation that will help us describe plane waves propagating in any arbitrary direction, and that's going to be part 3 of this lecture.